So let's talk about one of the trickiest things in research, figuring out if one thing actually causes another. It sounds simple, but with real-world data, it's a minefield. Today, we're going to dive into a tool that's both a lifesaver and, well, a landmine: statistical control. Let's get into it.
Here's the plan. We'll start with a really surprising link. Then we'll play detective and unmask a hidden variable that's messing with our results. After that, we get to the juicy part, when trying to control for things actually makes your analysis worse. And we'll wrap it all up with a clear rulebook and the big takeaway for your own work.
All right, so let's set the stage. Picture this: you're a sports scientist, and you're trying to figure out the real deal between an athlete's lean muscle mass and how fast they can run. And that leads to the big question. I mean, it seems like a no-brainer, right? More muscle, more power, faster times. But is the story the data tells us really that straightforward? Well, when you first pull up the data, whoa, the link looks incredibly strong. The scatter plot shows this beautiful, clear trend. The more muscle someone has, the faster their sprint time is. If you were a coach, you'd be seeing dollar signs right about now. And the numbers really back that up, at least at first. The initial calculation says that for every single extra kilogram of muscle, you shave a whopping 61 milliseconds off a sprint. Now, based on that alone, you'd probably tell every single one of your athletes to start bulking up. But that would be a huge mistake. And here's where the story takes a turn. That first really convincing clue, it's actually leading us down the wrong path. There's something else happening behind the scenes, a kind of hidden variable that is totally messing with our results. And that sneaky variable has a name. It's called a confounder. Now, the definition here is absolutely key. A confounder isn't just some random third variable. It has to be a common cause of both the thing you're studying, in our case muscle mass, and the outcome you're measuring, which is the sprint time. For our athletes, that classic confounder is gender. This little diagram shows it perfectly. Gender acts like a causal fork. Biological differences on average affect how much muscle mass people have. And they can also independently affect athletic performance. It's a common cause that's influencing both of our variables. So what happens when we actually account for this? The numbers, they just crater. As soon as we statistically control for gender, which is kind of like comparing men only to other men and women only to other women, the estimated effective muscle drops from 61 milliseconds all the way down to just 22. So what's going on here? Well, the actual direct causal effect of muscle on speed is just so much smaller than it first appeared. What we've done by controlling for that confounder is we've blocked a sneaky backdoor path of correlation, which lets us see the true, more direct relationship much more clearly. Okay, so controlling for stuff is good, right? Well, not so fast. We just saw how controlling for the right variable saved our analysis. But now we need to talk about the danger zone, because controlling for the wrong variable can completely destroy it. There are two big pitfalls that researchers can fall into here, and they can actually create bias where there wasn't any before. The first is controlling for something called a collider, and the second is controlling for a mediator. All right, so a collider is basically the evil twin of a confounder. Instead of being a common cause, it's a common effect. Two totally separate things both cause this third thing, the collider. And here's the crazy part. If you control for it, you actually create a fake artificial link between its two causes. Let's make this real. Imagine we decide to control for an athlete's belief in their own ability. I mean, that seems plausible, right? Belief is related to performance. But just think about it for a second. Having more muscle might boost your belief, and totally separately, clocking a faster sprint time might also boost your belief. That makes belief a classic collider. And the result of controlling for it? It's a train wreck for our analysis. If we make this mistake, our estimate for muscle's effect tanks, dropping to just 10 milliseconds. We've introduced a massive bias that basically cuts our estimate in half and makes muscle seem way less important than it really is. All right, trap number 2 is the mediator. Think of this as the middleman in the causal story. Your cause leads to the mediator, and then the mediator leads to your outcome. It's a crucial link in the chain that explains how the effect happens. For example, say we want to know the total effect of gender on sprint time. We know that gender influences muscle mass, and then muscle mass influences sprint time. In this story, muscle mass is the mediator. If we control for it, we're basically erasing that part of the story, and we'd wrongly conclude that gender has a much smaller effect than it actually does.
Whew, okay, that was a lot. So let's boil all of that down into a super simple, actionable cheat sheet for deciding what you should and should not control for in your own research.
Honestly, this table makes it pretty simple. If a variable is a confounder, a common cause, you absolutely have to control for it. But if it's a collider, a common effect, you do not control for it. And if it's a mediator on the main causal pathway, you also leave it alone, at least if you want to understand the total effect.
Now, of course, there's a catch. This isn't a magic wand. Our ability to get this right depends on a few really important things. Like, we can only control for the confounders we've actually thought of and measured. We also have to be pretty sure about our theory of how everything is connected. And we have to fight that temptation to just throw every variable we have into the model, because that can easily backfire. So let's zoom out. What's the big idea we need to walk away with after all this? What's the main takeaway from our journey into statistical control? I absolutely love this quote from Julia Roher because it just nails it. Statistical adjustments aren't an automatic fix for messy data. They are incredibly powerful, yes, but they're tools that require some serious thought and judgment to use correctly. So, our job as researchers really comes down to this. We have to use our brains, our domain knowledge, and tools like these causal diagrams to draw out the map before we start crunching the numbers. The whole point is to try and make our analysis act more like a clean experiment by thoughtfully closing those backdoor paths while leaving the real causal pathways wide open. And I'll leave you with this question to chew on for your own work. The next time you see a correlation, ask yourself, what are the invisible confounders, the sneaky colliders, or the hidden mediators that could be pulling the strings behind the scenes? Because thinking carefully about them is the first, most important step toward finding the truth. Thanks so much for watching.